Hello class, this is CSE-4600, Section 62, Week 6, Fall 2024. This is going to be your Part 3 of Chapter 2. We still have quite a lot of Chapter 2 to go through still, but I would like to take this time to talk about two things, really. So, the first thing is this. When we have multiple processes running on a system and they have shared memory, we have the danger of having what are called race conditions, which is where we have, say, some variable in memory that two processes are trying to access at the same time, when we don't want that to happen because they might interfere with each other's operation. The other thing is this. Sometimes we need those processes to work together to solve a specific problem, so we need some means of what's called synchronization. So we're gonna continue our discussion on synchronization, starting where we left off with Peterson's solution. This was a software-based implementation of a solution of maintaining mutual exclusion between two processes. Basically, if one process is in its critical section, the other one, if it tries to access its critical section, it'll be caught in a busy waiting until it'll be stuck in a busy waiting until the other process tells it, hey, you're good to go now. After that, we're going to start looking at scheduling algorithms, and we're going to look at about 5 or so scheduling algorithms. There are quite a few scheduling algorithms out there. But let's begin our discussion where we had left off previously, and that is sleep and wake up. So, slideshow, from current slide. So, same slide as it was in the last video. Peterson's solution and those using either TSL or Exchange, they are correct, but they require a busy waiting. The problem with the busy waiting is this. If we have, in a busy waiting, you have a process repeatedly testing some condition until that condition is, well, met. The problem with that is it does unproductive work. So keep the CPU busy, but don't keep it busy with unproductive work. So let's look at this. The busy waiting that Peterson's solution requires actually has other problems beyond wasting CPU time. This problem is called priority inversion, and it works like this. Say there's a high priority process that is run whenever it's ready to run, and it takes precedence over low priority processes. At some point, a low priority process is at its critical section when the high priority process is ready to run. This makes the high priority process begin its busy waiting. However, since the low priority process is never scheduled while the high priority process is running, the low priority process is stuck in its critical section while the high priority process takes forever. That is called priority inversion. That's its own problem, and this is a problem that we can also get if we use busy waiting instead of other means of making sure. Yeah, so there are several problems with busy waiting, and it's not just the fact that we are doing unproductive work. We might have a scenario where we trick the system into getting a high priority process waiting forever on a low priority process. So, we're going to consider a problem in computer science called the producer's consumer's problem. It's also called the bounded buffer problem. So we have two types of processes, or maybe we can just have two of each type of process. We have a producer, which puts data into a shared buffer, and a consumer, which takes data out of a shared buffer. So we're going to start with the scenario of there's one of each type of process. That's easier to work with. So trouble arises when the producer tries to put something into an already full buffer. So this buffer that's full of data, a producer puts data into the buffer, and the consumer tries to take data out of the buffer. So if the data that the producer is trying to put, there's no room for it, really the solution is to have the producer go to sleep, and once a consumer comes in, takes a piece of data out, it will wake up the producer and say, hey, wake up, it's time for you to restock. Likewise, if the consumer tries to take something from an empty buffer, it will go to sleep, and when the producer comes in to add stuff to the buffer, it will wake up the consumer and say, hey, wake up, there's something in the buffer for you to take now. So, the solution sounds simple enough, but of course we're gonna have more race conditions. We need a variable called count to keep track of the number of items in the buffer. Now, if the producer tries to add something to the buffer, it first tests the count. If it's at the maximum of some numbers, say there's a maximum of 10 items in the buffer. If it's at the maximum, it'll go to sleep. If not, it will add an item to the buffer and then increment the count by 1. Likewise, if the consumer tries to take something from the buffer, it will test the count first. If it's 0, it'll go to sleep. If not, it will take an item from the buffer, then decrement the count by 1. So this count basically keeps track of, well, how many things are in the buffer. So we're assuming there's room for 10 items in the buffer. The producer checks the count, makes sure there's room to add stuff to the buffer. Likewise, the consumer checks the count also, makes sure there is something to take from the buffer. If neither case is true, then the processes will go to sleep to be awakened by the other process. Of course, both processes check on whether the other process is asleep and also calls wake up if that's the case. So if one process tries to do something at the buffer but can't, it goes to sleep. The other process comes in, does something with the buffer, and wakes up the sleeping process. Sleeping process. Not Sleeping Beauty, sleeping process. So the code for the producer's consumer's problem might look something like this. Note that there are no sleep and awake routines in the standard C library, so these would be provided by the system itself. However, there is still a problem with this code here, and it is access to count is unconstrained, so we have the potential of a race condition again. And it's much like the same scenario with the printer daemon and the spool directory. So consider this scenario. The buffer is empty, and the consumer has just read the count to save it with 0. The scheduler then decides it's now the producer's turn to start running, and the consumer stops running. The producer adds an item to the buffer, increments count, and notices it's a 1. The producer reasons that the consumer must be sleeping, so it calls wake up. So what happened is this. The consumer, it wasn't asleep the whole time. Rather, the scheduler decided it was time for the producer to start running, so the consumer, it's not asleep. It was put into the waiting queue by the CPU scheduler. So now, the producer is gonna send a wake-up signal to the consumer when it thinks it's asleep, when it's not. So this wake-up signal is lost. The consumer never gets the signal. So when the consumer runs again, it will test the value of count, see it's 0, and go to sleep. Eventually, the producer will fill up the buffer and go to sleep as well. And now, with both processes asleep, neither of them can wake each other up. So this is the problem here. If a process tries to wake up the other process and it thinks it's asleep, it might not be asleep. It might be in the waiting queue for the CPU. So we need some way of saving that wake up signal. That's a problem here. And it turns out there is a way to do that. It's called a wake-up waiting bit. Basically, when a wake-up signal is sent to the process, while it is still awake, the bit is set. If a process were to go to sleep while this bit is set to 1, the process will stay awake and the bit is set to 0. This way, the wake-up signal isn't lost. And we clear this bit by the consumer with every loop iteration. The problem is this, and it is what happens if we have more than one of each type of process. We could just add multiple wake-up bits, but Edsger Dijkstra found a way to do this without requiring any other wake-up bits. And it's basically this. What if we could save those wake-up signals? So we sent a wake-up signal to a process that was presumably asleep but was in the waiting queue for the CPU. Because remember, we are assuming there's only one CPU core on the system. Only one process is allowed to run at a time. If the consumer isn't running, then the producer is. If the producer isn't running, the consumer is. In this scenario, neither process is able to run it. In this scenario, neither process can run at the same time. But then again, we can't have them run at the same time and have them both access their critical sections at the same time anyway. But the problem is this. We tried to wake up a process that we thought was asleep, but was not. And when we did that, we lost a wake-up signal. Which meant that when one process went to sleep, we broke the pattern of sleep and wake up. So if we lose a signal for wake up, we might have all processes go to sleep, which is not good. So Edsger Dijkstra suggested that an integer variable to count the number. He suggested using an integer value to count the number of wake-up signals saved. So this would become its whole new variable type called a semaphore. So a semaphore is just a thing that signals, which is what this navel-looking thing here, these balls on strings, this is a semaphore. It's a thing that signals. So this signaling thing, this value, this semaphore, can be a 0 or a positive integer. That indicates how many wake-ups were saved. So if a producer tries to send a wake-up signal to a process that might not be asleep yet, instead of that signal being lost, it's going to be saved. We also have two new operations here. Semaphores have two new operations called up and down. These are generalizations of sleep and awake. The down operation checks to see if the value is greater than 0. If so, it decrements the value and it continues. If a process calls down and it is 0, then the process that called down goes to sleep and it won't complete its down operation for the moment. The up operation increments the value of the semaphore. If a process was sleeping on that semaphore, unable to complete an earlier down operation, when another process calls the up operation, that other process is waken up and allowed to complete its down operation. And if there are multiple processes sleeping, then only one of those processes is awoken, possibly chosen at random, or maybe possibly chosen by process ID. And the thing about the up and down operation is they are done as a single operation that cannot be divided into smaller operations, and it cannot be interrupted by anything else. This is an atomic operation. Atomic in the sense that you cannot divide it into anything smaller. Atomic meaning indivisible. Not atomic meaning you're gonna get blasted by nuclear radiation. Also, you might see V and P instead of up and down. These are from Dutch terms that mean make higher and try. So let's try to solve these producers consumers problem using semaphores. So we might have modified code that looks like this. So the operations up and down are implemented as system calls, where the operating system briefly disables all interrupts while it performs these operations. If there are multiple CPUs, then each semaphore must be protected by a lock variable to ensure that only one CPU can read the lock variable at a time. So, of note is the fact that we have 3 semaphores here. 3 semaphores. One called full to indicate the number of buffer slots that are full, one called empty to indicate the number of buffer slots that are empty, and one called mutex. This is a binary semaphore because it can only ever be of one of 2 values, 0 or 1. So, this binary semaphore, we use this to ensure mutual exclusion. You're either allowed here or you're not because it's already in use. So, here's the thing. As long as each process calls down before entering its critical section, followed by up after leaving its critical section, mutual exclusion is guaranteed. And it's through the use of semaphores that we can get synchronization to happen. Synchronization meaning we have multiple processes working together to solve some problem, and we need to make sure that they are synchronized with each other, that they are doing these steps in the right order. If a semaphore's ability to count is not needed, and instead it's used to indicate one of 2 states, locked and unlocked, then we have a simplified version of that semaphore. It's called a mutex, short for mutual exclusion. In theory, we can represent a mutex using a Boolean value, so 0 or 1, but in practice it's just an integer value that's either 0 or 1. A mutex has 2 procedures alongside it. One is called mutex lock, so when a process needs to access a critical section, it calls mutex lock. So basically, think of a mutex lock as a physical lock that you use to, say, lock a door behind you. Imagine a critical section as a special room with controls inside that a process must operate, and only one process is allowed in the room at a time. On that door and into the room, there is a lock on the door. A process needs to check that lock, make sure it's unlocked. If it is unlocked, the process can enter the room and lock the door so that no other processes can enter. So now we're imagining this critical section as a special room that needs to be locked. If another process tries to enter its critical section, say it's trying to open the door also, it's gonna first check the lock to make sure it's unlocked. And if it is, that process is blocked. It's going to be blocked until the process inside unlocks the door and tells the waiting process outside, hey, it's your turn. When a process exits its critical section, it calls mutex unlock. If another process is blocked because the mutex is locked, that process is unblocked and it can enter its critical section. Due to their simplicity, we can implement mutexes in user space, provided that we have the TSL or exchange operation, the TSL or exchange instruction as before. So we have these 2 routines implemented using some sort of assembly code. Mutex lock, TSL register mutex, compare register to 0, is it 0? Jump, if it was 0, mutex does unlock, so return. So jump to OK and return to caller, critical section where clearly entered. If not, call thread yield, mutex is busy, schedule another thread. And then try again later. And then try again, jump back to mutex lock, and then return to caller when we're ready to go again. And then mutex unlock, move a 0 into the mutex, and then return to caller. So it's much like the code from earlier where we had the busy waiting, except we don't have that anymore. Instead of a thread being caught in a loop of checking a value in a lock over and over and over again, instead, thread yield, remember that is called to have a thread release the CPU so that another thread can use it. So, if a thread would be blocked, it just gives up the CPU so another thread can run in the meantime. I really hope that a lot of this is making sense to you, by the way. That we have processes, or I guess we should say threads. It's like, I guess some confusion is we have processes, we have solutions for processes, and then we have solutions for threads. They work in much the same way, but with threads, they're kind of easier to work with in the sense that we don't need to set up shared memory between threads, because with processes, each process thinks it has the computer to itself. To get multiple processes working with one another, they need to set up areas of shared memory so they can pass values between one another. With threads, shared memory is a given, because if there are multiple threads that are part of the same process, then yeah, they are going to share memory already. And that's the thing about processes. They share a lot of the same memory. It's like that train analogy I gave the other week, where one thread would be a different person building up one of the cars of a Lego train. Additionally, new user threads have no clock signal to... there's no clock... The other thing about processes and threads is there is a CPU scheduler and a clock that are working together to choose processes to run at any given time. We don't have that signaling mechanism on the level of threads. So if a thread needs to give up the CPU to another thread, we as a programmer, we need to provide that signal. If a thread tries to acquire the lock, it will loop forever and never acquire the lock, since no other threads are allowed to run. Okay. User threads have no clock signal when other threads should run. If a thread tries to acquire the lock, it will loop forever and never acquire the lock, since no other threads are allowed to run. So we need a means of signaling the threads, hey, it's your turn to run. With mutexes, instead of busy waiting, a thread that's unable to acquire the lock calls thread yield, giving the CPU to another thread so it can run in the meantime. Okay, so the problem with this previous code is that there's no means of telling threads that it's their time to run. With here, there is. With mutexes, if a thread can't enter its critical section because there's another thread, it will give up the CPU core to another thread that is ready to run, so that way there is something running in the meantime. Keep the CPU busy. I'm just thinking about how this could extend to our train analogy, our Lego train analogy, so give me a minute. Okay, I think I have an analogy. So, so these Lego trains that I have, here, they have what's called, well, wheels. So imagine if there was a separate instruction manual for the wheels of this Lego train. So we have to attach the wheels to here. If that was its own instruction manual for some reason, then the critical section would be reading that manual. And the one thing about reading that manual at the level of computing is this. Depending on how that manual is set up, we cannot open the manual onto two pages at the same time. So it may be the case that only one process might be able to open the manual at the time. So if it's the case that we have one Lego builder building the train wheels, but another Lego builder needs to use those same instructions. If that other builder can't get to the instruction manual for the wheels because it's in use, then the idea of calling tread yield would be like this. Instead of this. I need to build the train wheels. Sorry, no can do. I'm already building the wheels. Okay, in that case, I'm gonna go build the train station instead. That's the idea behind tread yield. Instead of waiting for that resource to free up, you just do something else productive in the meantime. So that's what's going on here. If we are building out this Lego train and someone else is using one of the instruction manuals to build some subcomponent of the train, instead of waiting for that manual, one of the builders just builds something else in the meantime that also needs to be built as part of the set. So I hope that makes sense to you, by the way. I really hope that this makes sense to you. There is one caveat to all of this that I mentioned. So, as I've said quite a few times already, threads have no problem accessing the same mutex, since they have processes that have multiple threads. The threads that are part of the same process are all able to access the same memory, so they have no problem sharing memory. The problem is when we have processes trying to talk to other processes. Their address spaces are different. They are disconnected. They're disjoint. How do we get processes to share a mutex? Well, there are actually a few solutions. The first solution is to have the semaphore be stored in the kernel, meaning we can only access the mutex as a kernel, as a system call. However, most operating systems, including Windows and Unix, have means of, they already have a way of having processes share stuff between one another, share address spaces. So we could have it set up so that we have a mutex being shared between two processes, even though their memory spaces are disjoint, disconnected. And if all else fails, processes can just use a shared file. So even though this would be much, much slower than accessing memory, because reading and writing to a file is going to be way slower, we could just communicate between two processes using a file. So we can just write to the file, process 1 is in its critical section, and that would tell process 0, okay, I'm going to wait. So there's a interesting solution. So there's an interesting interesting alternative to mutexes, and it's called a futex. So let's go back to that real quick. So the thing about a spin lock is they are wasteful if we are waiting for a long time. But if not, then they're still quite fast. If there's much contention, it's more efficient to block the process and let the kernel unblock it when the lock is free. However, if it's little contention, then switching to and from the kernel becomes an expensive operation. So the idea is this. Excuse me. If a process tries to acquire a lock, if a process tries to enter its critical section, but it can't, and it enters a busy waiting. If the wait is short, then there's really no harm to having a spin lock. However, if it's going to wait for a long time, then that process is going to do a lot of unproductive work. To prevent that, it's more efficient to have that process be blocked and then unblock it when the lock is free. That requires calling a system call that relinquishes control to the kernel to have that unblock block operation happen. However, whenever we do this, whenever we have the kernel get involved, that has its own overhead. And we are trying to... when we have a spin lock, the idea behind a spin lock is that we don't have to call the kernel to block and unblock a process. Which is good if we know that the busy waiting won't be for that long. However, if it turns out to be that long, then we need to call the kernel and say, okay, we need you to block this process. So that's what mutex tries to do. It's a fast user space mutex provided by Linux systems that implements a mutex without calling the kernel if it has to. So this is a fairly short section because I want to get into our next section, that is mutual exclusion mutexes in pthreads. So pthreads provide several functions for synchronization, including a mutex variable. We create a mutex using pthread mutex init, and then if we don't need it again, if we don't need it anymore, we call pthread mutex destroy. We create a mutex by calling... No. We create a mutex using pthread mutex init, destroy it using pthread mutex destroy. If you want to lock a mutex, then we call pthread mutex lock. If it's already locked, then the thread that called it will be blocked. However, instead of blocking, we can instead call pthread mutex try lock. That returns an error code instead, in case we ever want to do busy waiting. Finally, pthread mutex unlock unlocks a mutex and releases a thread if there's at least one thread waiting for it. So this is how we get synchronization to happen at the level of pthreads. So we have mutex locks that threads can acquire lock, and if another thread tries to acquire the lock, it will be blocked until the thread that was using the lock calls unblock. There is another mechanism for synchronization, and it's called a condition variable. And there are five functions related to that. Whereas mutexes are good for allowing and blocking access to a critical section, what a condition variable does is this. It allows threads to block if a certain condition is not met. So pthread condet init and condet destroy are for creating and destroying condition variables. The primary operations for condition variables are pthread condition wait and pthread condition destroy. Pthread condition wait and pthread condition signal. These are both atomic operations. Wait blocks the calling thread until another thread calls signal. The blocking thread is often waiting for the signaling thread to do some work, release a resource, or perform some activity. Only then can the blocking thread continue. Also, if there are multiple blocked threads, then we use pthread condition broadcast instead. So, condition variables and mutexes are always used together, such as with the producer-consumers problem. So if we use condition variables as part of our solution to the producer's consumers problem, then we might have code that looks like this. So let me just put my camera out of the way. So one thread tries to lock a mutex. If it can't do that, then it instead waits on a condition variable. Eventually, another thread will signal, and it can continue. It's for this reason that the mutex lock itself is one of the parameters for pthread condition wait. And I'd like for us to try this sometime soon, maybe as part of your next lab. We'll see. It should be noted that condition variables, unlike semaphores, have no memory. If a signal is sent to a condition variable on which no thread is waiting, the signal is lost. So care should be taken not to lose these signals. So, looks like semaphores and mutexes make inter-process communication easy, right? Well, there's still a problem. It's still possible to screw up, calling up and down. We might call it the wrong number of times. We might call it the wrong order. Or we might just forget to call one of these functions at all. If we do that, then we break our mutual exclusion rules that we've been trying to establish. And if we do that, remember that scenario when one process tried to wake up another sleeping process and the signal got lost, and then both processes eventually went to sleep? That is called deadlock, where processes are blocked and they stay blocked because there's no way to unblock them. This results in no work being done. If we screw up calling up and down, then we might get deadlock where no processes are able to proceed with their work because they are blocked and there's no way to unblock them. And we're going to get to deadlock in quite a bit as well, so maybe not quite yet. So the thing about a monitor is this. It is a higher level synchronization primitive. So Brian Hansen and Hoare, H-O-A-R-E, Hoare, I don't know how you pronounce. I don't know how you're supposed to pronounce this, by the way. So these two proposed a higher level synchronization primitive called a monitor. It is a collection of procedures, variables, and data structures grouped together in a package or module. Processes can call a monitor's procedures, but they can't access anything that's inside. A monitor has one important property for enforcing mutual exclusion. Only one process can be active inside a monitor at any time. So a monitor is just a thing that you write using a programming language. So the compiler knows that they're special and can handle calls to monitor procedures differently from other procedure calls. When a process calls a monitor procedure, the first few instructions of that procedure checks whether another process or other processes are checks whether another process is currently active within the monitor. If so, the process is suspended until the other process leaves. And if not, then the process enters. With a monitor, it's the compiler that's arranging for mutual exclusion. This reduces the chances of something going wrong. The programmer writing the monitor doesn't even have to be aware of how the monitor arranges for mutual exclusion. All the programmer needs to know is turning the critical sections into monitor procedures will enforce mutual exclusion. We still, however, need a way to block processes when they can't proceed. This is done by introducing condition variables plus two operations called wait and signal. When a monitor procedure finds it cannot continue, it does await on some condition variable. This causes the calling process to block. If a process was previously prohibited from entering the monitor, it can enter now. This process can perform a signal on the condition variable the previous process was waiting on. So there are a few caveats with trying to write a monitor. H-O-A-R-E proposed letting the newly awakened process run, suspending the other one. Hansen's proposal required a process doing a signal must exit the process immediately. This means the last thing a process can do is in a monitor is signal. This is the implementation that the book goes with, by the way. So, yeah, if multiple processes are waiting on a condition variable, only one of those processes is awakened. So, this following pseudocode is a monitor for the producer's consumer's problem. Note the use of wait and signal. It's like that of sleep and wake up, except with sleep and wake up, one process may try to go to sleep while another process may try to wake it up. This doesn't happen with a monitor. And the thing about a monitor is this is a thing that you can write with a programming language such as Java. Java has a synchronize keyword which can be added to a method declaration. Oh, and by the way, functions in Java are called methods. I've been using the term procedure in lieu of the term function because that's what the textbook uses. Every time I say anytime I say procedure, it might be a function. But I say might be because simply put, some programming language many programming languages call things by different names. So in C++ it's called a map, but in Python it's called a dictionary, I think. All you know is a map, a dictionary, and an associative array are really all the same thing. Java calls functions methods, and so does C#. Also note that Java doesn't have condition variables, so wait and notify operate like sleep and wake up without the danger of race conditions. So the problem with monitors, and they still have problems too. Monitors are a programming language concept, so the compiler must recognize them and arrange for mutual exclusion. And the thing is, most programming languages, nor their compilers, even support monitors. So if you want to write a monitor to arrange for mutual exclusion, you need a language that supports it, such as Java. Also, these languages the languages that wouldn't support monitors wouldn't support semaphores either. However, assuming a semaphore-based operating system, these routines could just be added as assembly code to the relevant libraries. Finally, both monitors and semaphores were made with one or more CPUs that access a common memory. This does not work with a distributed system because each CPU will have its own private memory. So, the use of a monitor, and these are the problems. You need a language that supports it, and you can't use it on a distributed system where each CPU has its own memory. If we have multiple CPUs sharing the same memory, then it's fine. If we have each CPU with its own memory, then that's a problem. And a distributed system is merely a network of CPUs, each one with their own memory. So basically a group of computers all connected to a network, all talking to one another to solve some problem together. So we get to message passing now. So the primitives discussed so far are insufficient for exchanging information between machines. So far, we were talking about means of synchronization between processes and threads that are on the same machine. Once we get to processes talking to processes on different machines, then we can't use things like shared memory anymore, because how can they share memory if they're on two different machines? We need message passing instead. So we need two primitives, send and receive. One sends the message to a given destination, the other receives a message from a given source, or any source. So like semaphores and unlike monitors, these are system calls rather than language constructs, and we can make them into library procedures. So send, as I said, sends a message to some destination, receives a message from a given source. A process that tries to call receive, it can block until a message arrives, or it can return immediately with an error code. So imagine if I just left right now to check the door to see if there was a package from Amazon. But I come back empty-handed because I never ordered a package. That's the error message I'm talking about. So send sends a message, receives a message. So if a process calls receive, what can happen is one of two things. Depending on how it's implemented, it can either be blocked and it will keep waiting and waiting and waiting until it gets the message, or if it doesn't block, then it'll just return an error code saying, I didn't get the message. There are some design issues unique to message passing. messages can get lost in transit. So to protect against this, the receiver can send an acknowledgement message back to the sender. And if the sender doesn't get one in time, it resends that message. However, the acknowledgement message can also get lost in transit, so the sender must be able to distinguish between old acknowledgement messages and new ones. Also, it's possible for a message to be sent to an imposter, so to protect against this, authentication is needed, ensuring whoever is receiving the message is the real deal, the intended recipient. And then sometimes, the sender and receiver might be on the same machine. So the thing about message passing is, if you have message passing between two processes on the same machine, it's going to be slower than if you had set up for shared memory. However, a lot of work has gone into making message passing efficient. So if we have the producers-consumers problem set up for message passing, the code might look something like this. So we use message passing for parallel programming systems, and one of them is called MPI, simply called Message Passing Interface. Oh, by the way, my camera's covering up the comments, though there really isn't much that you're missing out on. So here's the unobstructed code if you're curious. And finally, we get to another kind of synchronization mechanism called a barrier. Think of it like a traffic light. So processes are doing things, and they all need to arrive at the same time and proceed to the next step all at the same time. So processes complete their work at different times, they arrive at the barrier. Once all the processes are arrived, once all the processes have arrived, the barrier lifts, and all the processes proceed together at the same time. Pretty simple, right? So an example of how a barrier could be used is with matrix operations. If you've ever been lost on how matrix multiplication is, it's basically a lot of dot products. So the entries, if we have two matrices, A and B, and they are 3 by 3 matrices, their product is going to be the dot products of the entries in the product matrix are merely the dot products between the row vectors of the first matrix and the column vectors of the second matrix. So if we can if we can represent the first matrix as a matrix composed of 3 row vectors, A1, 2, and 3, and the second matrix as a matrix of column vectors, B1, 2, and 3, then the product matrix is basically every possible combination of dot product between one matrix's vectors and the other matrix's vectors. If you can do a dot product, you can do matrix multiplication. It might be a lot of matrix multiplication, but if you can do a dot product, you can do matrix multiplication. But I can understand that doing this, there's a lot of computations involved. So yeah, this is why we typically have computers do our matrix multiplication for us. And when they do, there are a lot of ways to speed it up, so we don't have to do one operation at a time. We can do like several at a time. So in this example, we might delegate each of these dot product operations to one process. The point is this: we cannot advance to the next step if this product is involved in some other computation. We cannot proceed to the next step until every entry in this product matrix has been computed. So that's what a barrier is for. It makes sure that we don't proceed to the next step until every process is ready to go to the next step. And now we get to the one thing I've been wanting to get to for a while: scheduling. This is an important aspect related to processes. When there are multiple processes on a computer system, and especially if there's only one CPU core available, we have something called a scheduler that decides which process gets to run by using what's called a scheduling algorithm. In the early days of batch systems, where input was on magnetic tape, well, technically it was on punch cards, but there was a machine that would convert the information on punch cards onto something that can be put on magnetic tape. In the early days of batch systems, the scheduling algorithm was simply run the next job on the tape. Multi-programming made this algorithm more complex because there were generally multiple users waiting for service, and the introduction of the personal computer changed all of this in two ways. Most of the time, there's only one active process. That's number one. Number two, computers have become so fast that the CPU is rarely a scarce resource. The limiting factor is not how fast the CPU can process input, but rather how fast the user can provide that input. On network service, multiple processes are competing for the CPU, so scheduling still matters. On all but the most powerful mobile devices, CPU resources are limited by what can physically fit in the device, and especially how long the battery can keep it powered. In addition to all this, the act of switching between processes, this is called a context switch, by the way, the act of context switching, that is an expensive operation also. First, the system was switched from user mode to kernel mode. Then the state of the current process is saved. This includes saving the contents of the registers. Some systems may also save the memory map. This is information regarding how to access memory. And then finally, a new process is selected and its state in memory is loaded too. Nearly all processes alternate between bursts of computing and I/O requests. These are requests to read from, or write to a file. When the system for I/O completes, then the CPU can continue computing until it needs another I/O request. I/O in the sense means a process is blocked because it's waiting for an external device to complete its I/O. It's just that sometimes we have I/O operations that don't count as an I/O operation because it involves the CPU in some way. By I/O, I'm talking about something like reading from, or writing to a file, such as I need to save this file, or the program is automatically saving this file periodically. That's what's meant by I/O. So, the thing is this. We can generally class processes under two categories based on how much more of what they're doing. If a process is doing a lot of computation, if a process is doing a lot of computation, then it's going to be characterized by what are called CPU bursts that are long. So long CPU bursts. So it's going to be computing for a very long time. Computing, and then it stops because it needs to write to a file. But once that's done, it's going to compute, and then it's going to have to write to a file again. So that's what's called a CPU-bound process, or a compute-bound processes. These are processes that compute in long bursts. If, on the other hand, a process can only do a little bit of computing. Okay, I need to read from a file again. And now I have to wait. And now I got the information I need, so I need to compute, but I need another value from the file again. So I have to wait. Okay, I got it. Compute, no, wait, I need to read the file again. This is called an I/O-bound process. These have more frequent CPU bursts, but they're shorter. So that's a general way we can classify these types of processes. They either have large but infrequent CPU bursts, or they have a lot but short CPU bursts. Also take note of this. The faster a CPU becomes, the more likely it is for processes to become I/O bound. So basically, the faster the CPU becomes, the more likely it's going to become I/O bound because, well, CPU technology has been advancing, but not storage device technology. Yes, we have hard disk drives. Yes, they're slow. Yes, we do have SSDs. But even that has its own drawbacks. And yeah, we also have the M.2 SSDs. And I know this because I had to swap my motherboard and my SSD for a larger one. These, all I know is that these things directly attach to the motherboard. Are they any faster than a regular SSD? I would hope so. So anyway, if the CPU is becoming faster and faster and faster, and reaching, say, 5.7 gigahertz, which is insane, by the way, then the only thing holding it back, apart from how fast the user can input data into the computer, is how fast it can get data from a hard drive. So we need research into making sure that the I/O can keep up with the CPU. Because what's the point of having a fast CPU if you can't read from a file fast enough? There are a variety of situations in which scheduling is needed. When a process is created, which one's first, the parent or the child? When a process exits, which process should run next? When a process blocks on I/O, which process runs next? When an I/O interrupt occurs, it means an I/O request a process has made is complete, and that process that had made that request is ready to run again. Should it run again, or should some other ready process run instead? If a hardware clock periodically interrupts the system at some frequency, a scheduling decision can be made at every clock interrupt, or say every 5 clock interrupts, for example. Scheduling algorithms can be divided into 2 categories regarding how they deal with clock interrupts. The first one is non-preemptive. Basically, a process is selected to run until it can no longer run. It waits, so that means it waits for I/O or releases the CPU. And it will run in non-preemptive scheduling. In non-preemptive scheduling, a process is allocated to a CPU, and that process will run. It'll keep running until it can't run anymore. Only then will another process run. And especially if a clock isn't available to signal interrupts, then non-preemptive scheduling might be your only option. With preemptive scheduling, a process is selected to run for some amount of time. After that, it's suspended, it's removed from the CPU, and then another process is selected to run. This requires a clock interrupt. So, we have non-preemptive scheduling and preemptive scheduling. Non-preemptive means a process runs until it can't run anymore. Preemptive means processes basically kind of take turns in a way. Or, no, that's round robin. We'll get to that in a little bit. Preemptive means a process is selected to run for some amount of time, and then when time's up. When time is up, another process is selected to run. Unsurprisingly, there are different scheduling environments for different computing environments. There are different scheduling algorithms for different computing environments. So, batch systems, interactive systems, which includes servers and real-time systems. So, regardless of the type of system, it's necessary to have an idea of what's expected of a good algorithm. So, of these, there are goals that should be met for all types of systems. So, the general goals are fairness. Comparable processes should get comparable service, except in cases where we have a high priority process that has something that must be executed as fast as possible. Policy enforcement. Related to fairness, whatever policies are on the system must be enforced by the CPU scheduler. Oh, and keep the system busy. I say keep the CPU busy, but also keep the I/O devices busy. More work gets done if the CPU and related I/O devices can be kept running all the time. So these goals are related to batch systems. Throughput. This is the number of jobs that get completed per, say, this is the number of jobs that get completed per unit time. Say, jobs completed per hour. Higher is better. Turnaround time. This is the average amount of time between when a job is submitted and when it's completed. Lowest is better. Lower is better, but there are some caveats to that. CPU utilization. It's actually more than just to keep the CPU busy. Although throughput and turnaround times are important, this metric is actually useful for knowing when it's time to upgrade your system. So here's those little caveats regarding throughput and job size. Basically, if you have multiple jobs coming in and they are of all varying sizes, if you just want to minimize turnaround time, you might start prioritizing all the small jobs over larger jobs. And in the extreme case, the large jobs might never get completed at all. So if you want to make sure you complete as many jobs as possible, then you don't want to minimize turnaround time by neglecting all the large jobs. Because you need to do all the jobs, not just the small ones. For this reason, a scheduling algorithm that maximizes throughput may not necessarily minimize turnaround time. Okay, so these are the goals for interactive systems. Basically, response time, this is the time between issuing a command and getting a result. Lower is better. Proportionality. Although users have an inherent but often correct idea of how long tasks should take, this expectation should be met. And for real-time systems, meeting deadlines. When it comes to processing incoming input, the system should make sure that that data is processed on time, or else data may be lost. And predictability. When it comes to playing a video, missing a deadline occasionally will not result in fatal error, but it will make for a less than ideal viewing experience. Processes should be regular to avoid this. So there are quite a few scheduling algorithms that we're going to look at. So we're going to look at 3 related to batch systems, and then 2 more related to interactive systems. So the first one is called first come, first served. This is the simplest non-preemptive scheduling algorithm. Basically, whatever process comes in and falls in line for the queue for the CPU, that is the first process we're going to run. And the next one that falls in line after that, that becomes the next process that we run next. And because this is a non-preemptive scheduling algorithm, it will keep running that process until it stops running. Any processes that enter after that must wait in a queue to wait for their turn. So the advantage of first come, first served is that it's easy to understand and easy to implement. The disadvantage is this: processes must wait for a turn. So let's say we have 2 processes. One arrives first and becomes the first process to run on the CPU. The next process comes in and it's waiting for its turn, which might not be all that bad, but consider this. What happens if the first process were running? What if that's an I/O bound process? What if it's running, it needs to read a file? And then we have to wait. And then it's running again, and then it has to read from a file again. That would sound, for lack of a better word, unfair to other processes that are waiting. Because if that process is waiting for I/O, well, wouldn't it be a better idea to just remove that process, put it back in the queue, and have that other process come in to run? Well, that is what round robin does, but we're not doing that just yet. We're not at that point yet. And because FCFS is non-preemptive, that process will stay on the CPU, even if it's not doing any computation. However, what if we knew beforehand that first process was going to take like 1,000 milliseconds to finish its work, and then the next process that came in, what if we knew that's going to take only 5 milliseconds? It would make more sense to do that first job first, so that way the next job wouldn't have to wait all that long. Because in the scenario where we have one process doing a lot of work, and it's unfair to the next process that only has to do a little work. If we know how long these processes will take to run, then it would be more effective to simply just arrange these processes so it's the shortest job first that we're running. And that's our next scheduling algorithm. Shortest job first. If we knew in advance how long processes can run for, then we can minimize turnaround time for all processes by running the shortest job first. So, the advantage is this. It is optimal. It will provide the lowest, it will provide for us the lowest turnaround time out of all possible scheduling algorithms. However, for this to be optimal, we need to know ahead of time how long each job will run for. And although it's not emphasized in this textbook, it's emphasized in the other operating systems textbook. That's the one with the dinosaur on the cover. Because of this, we cannot implement SJF in practice because we don't know how long these jobs will run for. There's a similar scheduling algorithm. If we know how much longer it takes for a job to finish, we can instead assign whichever job has the shortest remaining time next. And much like SJF, we need to know this information in advance. So if two processes arrive and we know the first process only needs to do like 5 milliseconds worth of work, and the next one needs to do like 3 milliseconds worth of work. If we know this information in advance, then we'll just let the 3 millisecond process run next. Right now I'm thinking about how checkout lines have an express lane for 15 items or less, or I guess grammatically correct would be 15 items or fewer. That's what's meant by shortest job first. And the idea behind the express lane is this. We are scanning fewer items, that means we can get through more customers faster. I'm just imagining how chaotic it would be if people fall in line for a grocery at a grocery store for the cashier. Would it be better or worse if customers arranged themselves by how full their basket was? By how full their basket was might be a terrible metric, because a 40-pack of water, it's gonna take a lot of space compared to like dozens and dozens of cans of beans. So the water, even though that takes a lot of volume, that's only one item to scan. In the case of like cans and cans of beans, you have a lot of items to scan. So now we have that problem too. Anyway, for scheduling in interactive systems, we're gonna look at the first two for now, and then we're gonna continue our discussion in the next set of slides for these other scheduling algorithms. So scheduling in interactive systems, we're gonna look at round robin and priority scheduling. So round robin is one of the simplest, fairest, and widely used scheduling algorithms out there. Simply put, processes take turns running on the CPU. They'll run for some amount of time. They'll run on the CPU for some amount of time, and this amount of time is called a quantum. And once that time is up, the CPU is preemptive. It's preempted and given to another process. So of the two scheduling algorithms we've looked at yet, well, three actually, of the three we've looked at already, round robin is the first preemptive scheduling algorithm we're looking at. Basically, processes take turns on the CPU. So processes fall in line in a queue, and whichever process is at the head of the queue, that's the process that will run first. That process is going to run for some amount of time until time is up. When that happens, that process is put in the back of the queue, and then it's the next process's turn to run. Once that's up, that process goes back to the queue. In the back of the queue you go. Back of the line you go, and then the next process runs. And then back in the line you go, next process runs. And they basically keep track using a queue, and they basically take turns on the CPU. So these processes take turns on the CPU running, and then next, running, next, running, next. And they do that until processes finish running. That means they've done all their work, and then the CPU is free to do the work of everyone else's work, if that makes sense. So the one variable about how round robin works is how long do we make that quantum? So due to the overhead related to context switching, a large quantum is recommended so you don't waste too much time on context switching. However, a large quantum may make an interactive system less responsive, so a smaller quantum is recommended. And if the quantum becomes too big, then round robin devolves into first come first serve. So let's say we have 3 processes that require 5, 7, and 3 milliseconds of time to do their work. If we set that quantum to like 1 million milliseconds, it's no different than first come first serve. If we set that quantum to 1 millisecond, then it will operate as it normally would, though 1 millisecond may be way too short. Give me a second. Sorry about that. I had to check on something. So anyway, with round robin, the one variable that we tweak is how long we make that quantum. Too short of a quantum, and we're doing a lot of context switching. Too long of a quantum, then our interactive system becomes less responsive. So we need to balance. You need to find a good balance of small quantum to avoid a lot of context switching, and large quantum to avoid a lot of context switching, and small quantum to make our system more responsive. So the balance here is something like 20 to 50 milliseconds. So priority scheduling. Round robin makes the implicit assumption that processes are equally important. Oftentimes it may be the case that a process with a mission critical job may need to run first without being interrupted. So in priority scheduling, each process has a priority level. Really, I don't like how the book talks about priority scheduling, so I'm gonna base it off of the other book. So basically, if you can imagine round robin, and all of these processes have the same priority. If a process comes in with a higher priority than anything else in the queue or on the CPU, if this is a preemptive system, if a high priority process comes in, then basically whatever process is on the CPU is taken out and put in the back of the queue. And then the high priority process, when it entered the queue, it had a higher priority than all other processes. So it's gonna end up going to the front of the queue. So when the CPU scheduler says, next, it's the high priority process that runs. So it's going to run. And let's just say that this process, when it comes to this high priority process, it's not preemptive. So it's gonna keep running until it stops running. So it'll keep running for a while, and then once it's done, the high priority process leaves, and then all the other processes that were waiting on the high priority process, they're now free to run on the CPU core now that the high priority process is gone. So basically, in priority scheduling, each process has a higher priority level. Whichever process has a higher priority is the one that runs first. If a process has a higher priority than other process is in the queue, it's moved to the front of the queue. If the scheduling algorithm is preemptive and the process at the front of the queue has a priority higher than the process currently running, then the currently running process is removed from the CPU, goes back to the queue so the high priority process can run. And we do have a data structure called a priority queue that we can use to implement this priority queue, by the way. Oh yeah, one confusing thing that can happen with priority levels is this. There's no standard as to whether larger numbers are high priority or smaller numbers are high priority. Some systems do it, a lot of systems do it differently. So we just have to figure out whatever standard our particular system is using, follow that. If it's smaller numbers means higher priority, then we go by that. So whichever system, if it's smaller numbers means higher priority, then whichever process has a smaller priority value, that's the high priority one. And again, we do have priority queues that will help out with this. So that is our foray into scheduling algorithms, which is something I wanted to get into for quite a while. We're not quite done yet. There are still a few scheduling algorithms left that we have to cover, and then after that, we'll see what comes next. Let me know if there's anything about this that you're still lost on, by the way. So that way, I want to make sure that everyone gets these concepts. I want to make sure that everyone gets these concepts in a way that makes sense, you know? So, if I may take this time to look into what we have next. Okay, so I have the book here, and we don't have much left in terms of what to go through next. So, we have a few more scheduling algorithms we're going to talk about. And then we're going to look into at least one, maybe two different interprocess communication problems. The first one is called the dining philosopher's problem. So this is a classic problem related to interprocess communication. So we have resources, and then we also have processes that need to use those resources. So yeah, that's all there is left to chapter 2, and I might squeeze in the last of that while we look into the next chapter. I'm not sure if we can get to memory management just yet, so I will say there is quite a lot that goes into memory management. I kind of like the other book better because it chops up everything into bite-sized pieces. That's why the other textbook with the dinosaur on it, on the cover, that's the Silver Slots textbook. That has like nearly 20 chapters, but all the chapters are grouped into parts, whereas this one has fewer chapters, but all the chapters are thick. It is, however, the same information, just arranged differently. So yeah, we don't have much left on chapter 2. So after that, we're gonna discuss our next chapter as outlined in the syllabus. So hopefully you hopefully you learned something here. Let me know if there's anything about this that you're still lost on. Oh yeah, your lab, you still have a lab. Let me know if you have any questions about that, and then if you need to talk to me about it, then yeah, we can schedule a meeting then. Alright, with that, I'm gonna end the video here, and then we're gonna look at our next topics after that. So, take care, and I'll see you in the next video.